This video investigates the idea of a maximally symmetric manifold or space and derives the Riemann equation for this space using the metric tensor and Ricci scalar. It also shows how these spaces must have a constant Ricci curvature scalar. And this video is an update to a previous video of the same name. Right, now, a space is homogeneous if it is invariant under any translation along any of its coordinate axes. So pick a direction, walk in that direction, and if your space looks the same, then it's homogeneous. Now, a space is isotropic if it is invariant under a rotation of any coordinate axis into any other coordinate axis. So stand still on the spot, turn around, and if when you turn around the space looks the same in all directions, then it's isotropic. Now, in an n-dimensional space there are n coordinate axes, and so there are n number of translational isometries if the space is maximally symmetric. So in 3 dimensions you'll have 3 axes, so 3 translational symmetries. In this same space there are n number of coordinate axes that can be rotated into n-1 other axes. Now, we don't count a rotation of, say, the x-axis into the y-axis as being different to a rotation of the y-axis into the x-axis. So the total number of distinct rotations will be n number of axes times n-1 other axes into which it can be rotated, divided by 2, so that we don't count our rotations of the same twice. So x into y is the same as y into x, so we divide the result by 2. For a maximally symmetric space, we can expect the following number of isometries: n translational ones, n times n-1 on 2 rotational ones, to give us a total when you do the algebra of n times n plus 1 on 2. So, for example, in the 4 dimensions of Minkowski space-time, there are 10 killing vectors, and the reason for that is 4 dimensions. You have 4 times 4 plus 1 is 5, 4 5s are 20, on 2 is 10. And that's made up of 4 translational isometries, and the 3 spatial and the 1 time, and 6 rotations. 3 of them are spatial rotations, and the other 3 are boosts, which are really rotations in Minkowski spacetime. So Minkowski spacetime is maximally symmetric. An n-dimensional manifold is maximally symmetric if it has n times n plus 1 on 2 independent killing vectors. Alright, for an n-dimensional manifold, the Riemann tensor is given by this object here, and we're using the 1 forms here, or covariant vectors if you like here, the lowered index, and it's the Riemann tensor times the covariant vector or 1 form, plus the torsion and the covariant derivative of the 1 form. In the absence of torsion, this part drops out and we're left with just this expression here, this equation here. Now, this result tells us when we differentiate the 1 form v in 2 different directions and then subtract the result from the same process, but in the opposite order, we end up with a non-zero result. That is because in a curved space, the basis 1 forms vary from point to point, and the end result is an object proportional to the original 1 form. In flat space, the result of this process is 0, because the basis vectors are constant from point to point, or the basis 1 forms constant from point to point, and so it all drops out to 0, but not in curved space. And there's a whole video on deriving the Riemann tensor on this channel, deriving the Riemann tensor except using vectors instead of 1 forms, and that shows the differentiation in 2 different directions gives you a non-zero result over here. Alright, so written in terms of a killing vector we just replaced the previous equation with the killing vector here, the lowered index A, or over here D. Now, or using the commutator, we have this object here, the commutator, K, acting on K, the killing vector gives us this object over here. And from a previous video, we also have this result here. Now, by applying the commutator to a derivative of our killing vectors, we will discover some interesting relationships that apply to maximally symmetric spaces. Alright, by inserting an extra covariant derivative factor into the previous equation, we can appeal to the law of associativity when carrying out the triple derivative of a killing vector. So covariant derivatives do not commute, but they are associative. So now we have, instead of the 2 covariant derivatives, we have 3, and over here, and we'll use associativity. So let's perform this operation, and then also first, that is, before performing this, and then over here, similar thing, let's do this first and then these two here. Now both expressions will produce the same result. So let's use this associativity property with the commutators as defined earlier, and let's begin to derive our first result. So here's a commutator, and del or nabla d ke, and writing that out, we have this, and then using associativity we'll perform this operation first, the ones in the parentheses, and we found from the previous video we have this result here. These two covariant derivatives acting on the killing vector here gives us the Riemann tensor and the killing vector, and same over here minus that. Now what we're going to do is use the product rule or Leibniz rule for this covariant derivative here acting on the material, the object inside the parentheses here. So first thing, derivative of the Riemann tensor times the killing vector plus the Riemann tensor times the derivative of the killing vector, and similarly for this bottom one here, for the second one here, over here, we have the covariant derivative of the Riemann tensor times the killing vector minus the Riemann tensor times the covariant derivative of the killing vector. When we do that, writing that out down here, removing the parentheses, this is our first result, and we'll be referring to this later on. Most of the video hinges on this and the next result we're about to achieve. So this is our first result here. Let's move on. Now, this is the beginning of our second result. So here's the commutator, and here's the covariant derivative of the killing vector, and we're going to act on that with the commutator. So that gives us this object here. And let's put in parentheses the bit we're interested in here, and then we'll have this double covariant derivative acting on that, acting on what's in the parentheses. Okay, so here we go. Product rule again. We're going to have the double covariant derivative acting on the covariant derivative times the killing vector plus the double covariant derivative acting on the killing vector times the other covariant derivative. So product rule or Leibniz rule in operation again. Same for the second line here. That's just this part here with a minus in front. And then what we'll do is come down a little bit further again. Here we are, this object here, and we will pick out, in other words, we're going to combine this term here, first term, and the third term, put them together like that, and then the second term and the fourth term will be combined like this, right? And when we do that, we find that this first terms 1 and 2 here gives us this object, and terms 3 and 4 here gives us this object here, and then we will have the we'll be able to swap the order of these two here. So it says the killing vector times the covariant derivative, that will be swapped to give us the covariant derivative times the killing vector, and I'm about to mount an argument to show why that's the case. Okay, so our second result that's of interest in this video is this one right here, this last line. That's the bit we're in. Now if you're a little bit worried about this killing vector times the covariant derivative and the claim that it's the same as this object here, then let me mount an argument for that over the next couple of slides. Alright, now to see why the killing vector times the covariant derivative is equal to the covariant derivative times the killing vector, let's just refer back to a result or a theorem that says given two constant vectors, we have the vector x is m times d dxi and y is n times d dxj. Remember, these act as basis vectors. So these directional derivatives, if you like, act as basis vectors for us, and they form a suitable basis. M and n are going to be constants, and then the commutator, or Lie bracket is of the vectors x and y is this object here, the scalar product with these minus in the reverse order. And let's write that out. What do we have here? This object here, so m d dxi acting on n times d dxj. I could put parentheses in there, but no need. Minus n times d dxj acting on the product here of this constant times d dxi. And what we'll find is when we carry out this partial derivative of this constant here, d dxi will be 0. Same over here, d dxj of m will be 0 as well. And then we'll have what we'll have is m times d dxi times d dxj. Then we'll have over here minus n times d dxj acting on d dxi, because the m has gone, disappeared. Now what we'll find is that's 0 if m equals n. So if both these constants are the same, then we'll find out that this will go to 0. It's no good having m being, say, the value of 10, n being the value of 5, well then that won't go to 0. But where m and n are the same value, if they're both 1 or they're both 15 or minus 2/3 or what have you, as long as they're the same, that whole thing will go to 0. And so the commutator of d dxi, d dxj is 0. In the case where you don't have m or n, then this commutator automatically is 0. Now, Killing vectors have the form k is k mu, the upper index here, times the basis vector d mu, or k mu d dx mu. Remember, this acts as a basis vector here. Now, if the metric is independent of a coordinate x alpha, then so if some metric is independent of a coordinate x alpha, then k mu is delta mu alpha, which is 0 if alpha doesn't equal mu, and 1 if it does. So we expect this to be a constant of 1. Now, some examples include k is dt. This comes from the Minkowski spacetime and also from the Schwarzschild spacetime. We have these, because time is independent of both metrics. We have a Killing vector in the time direction being this object here, these here, k1, k2, k3, 0. Or in the phi direction, the angular direction in both cases, the metric is independent of phi, and so we have this basis vector here. Notice the component k mu here is 1 here and 1 here. Now, another thing, at any point p on a manifold, any and every point, the covariant derivative becomes, at that point and only at that point, becomes the partial derivative. So we can replace the covariant derivative with the partial derivative at each and every point on a manifold. Because local to that point, the space is locally flat. We could refer to geodesic coordinates or normal coordinates, but that's not necessary. Just at a point P, just as when we stand on the Earth is no doubt curved, but from where we're standing, it looks around us looks very flat. Same thing with a manifold. Alright, so commutator of the Killing vector and the covariant derivative, k dot del minus del dot k, so put that in here, times 1 times d dxd, was only a 1 outside of d dxd for del here, at a point P, minus this, well we've already seen that this goes to 0, the whole thing, and so that implies that if this goes to 0, then k dot del is del dot k. And so if that goes to 0, as we've seen above, at any particular point P I should say, well then multiplying 0 by the metric is still 0, and so the metric times this is also 0. Obviously we can use the metric to lower indices, so from the contravariate down to the covariant. And so the metric times this becomes ke del d. It contracts on the mu and the mu there to give us e here, and as we've seen by this result here, that's also equal to this. And hence previously we're able to swap the order of those two. Alright, next bit. So our two results were, this over here on the right was our first result, and on the left here was our second result. They must be equal, so we've set them equal to each other here. Now what we're going to do is take all of them onto the one side here, so we're going to take all of this on the left over to the right here, so the whole thing is equal to 0, to give us a relationship that we can work with. So that leads to this object here, when we take it all over to the right. That's the bit on the left here, take over here, set it all to 0. What we're now going to do now is work through this, and we'll make some small changes here, and the small change comes up at this point here. This is a Killing vector, so we can swap the order of these two here, because del A ke plus del E ka equals 0, because that's the condition for Killing vectors. And so this, if we swap the order of these two, we get the negative, so that becomes a plus here. So the only change between the first line and the second line is the minus here to a plus. It's just making use of the Killing vector. It wasn't necessary working through this. You don't need to do that everywhere, but I have done it here, sorry, on the end here, but I didn't do it here, and the result still works out, as you'll see later on. Right, next line down, we're going to go further along here. This all stays the same, that's all staying the same, that is the same, that is the same, and over here I did I swapped this in the end, so del d ka swapped here, and that meant that that minus does become a plus, so it was contradicting what I said earlier, but I did do that here, and then for some reason unbeknownst to me, I've gone and swapped these other two back as well. But anyway, we'll see how that goes. It does actually work out, as you'll see as we go along. I could have left it as it was, and it still actually will work out. Now, next line down, this bit stays the same, and along we go here. And what I'm going to do here, I'm looking here with these last four terms to factorize out the covariant derivative times the killing vector, but I just want the same indices to do that. And one way I can do that is introduce the Kronecker delta. So what I would like to get is to make it all del A times kf. Well, I've got an f here, f there, and this c I can alter to an a by putting a Kronecker delta in there with an a up top, so this a and this a contract and becomes the c. So this is the same as this, or if you like, this gives us this. So it's still the same object. I haven't changed anything. Alright. Over here, the b and the f, I'd like to change that b to an a, so introduce down here the Kronecker delta, put the a where the b was, put the Kronecker delta with an a up top, so these two contract, and put the b down here, so that when I do perform the contraction, I end up with this. Same over here, I've got del A kd, but this time I'm going to put in where the d is under the k there, that index there, I'm going to replace with f here, and I'm going to and then I'll put the Kronecker delta in with the f up top and the d down below. The f and the f contract to give me d down here, so this becomes this. And then finally for the last one over here, del A, I want that, and ke, so, but I'd like to change that e to the f, which is what I do down here. So again, Kronecker delta, ef, del A, kf, and when I perform this contraction, I get this object here. So, next step forward. Alright, now all of which leads to this, plus all of this, and now I can factorize out the covariant derivative a index here times kf, so nabla del a, del subscript a times k subscript f, all 0. Alright, let's have a look at what we've got. So the first half of this equation contains all killing vectors, alright, this bit here, while the second half, this part here, contains the derivatives of the n times n minus 1 on 2 rotational isometries. So this one gives me this times all the killing vectors on their own, plus this one here. When I take the derivative of the killing vectors, it doesn't all disappear. Some of it will be non-zero. I'll give you an example in a minute. So what I'm saying is this thing best helps us arrive at some understanding of what maximally symmetric spaces are. Now, why did I need this bit here? Because some of the killing vectors when I differentiate will disappear and some won't. To give you an example, for example, the Euclidean plane is 2D and has a total of 3 killing vectors. The two translational ones are k1 is ex, k2 ey, and the rotational one is this one, x times ey minus y times ex. Now when I take the derivative of this one and the derivative of that, they disappear. They're constant ones, they disappear. When I take the derivative of this, say with respect to x, this doesn't disappear. Alright, this part does, but that doesn't. If I take the derivative of all of this with respect to y, then that disappears, but this doesn't. And so that's why we need that part there. We want to deal with the killing vectors and the curvature, and we want to see what we can find out about the symmetry of maximally symmetric spaces. So the first derivative of the translational vectors disappears while the rotational one does not. Okay. Alright, again we have just re-quoting the result again, so keep that in mind. Alright. Now if it is true that our killing vectors and their first derivative are non-zero, then it must be the case that the coefficients shown above in the parentheses are equal to 0. Well, Ka is not 0, and del Ka is not always 0, sometimes it's not. So the only way this thing can be true, this entire equation here, is if these coefficients in here and these in here go to 0. So if that terms in there and that in there, the entirety together goes to 0, this goes to 0, these coefficients go to 0, that satisfies the equation. So that leaves us with two equations, this one here equals 0, and this part here equal to 0. Alright, so let's deal with the second equation first. Alright, here we go, this part here, and I'll multiply through by an extra here, delta Ca, delta Ca, delta Ca, Kronecker delta Ca. Alright, why do that? Well, if you have a look here, notice that this is reciprocal to this, and this, if you like, is the inverse to this, and this gives us, the, if you like, the A and A contract, or C and C contract, and you're left with just Kronecker delta AA or Kronecker delta CC, and when you sum that across the n dimensions, you get the dimensions of the space, n, so this just gives us n. We have over here now A and A, one up, one down, so summation convention applies, you're left with Kronecker delta CB. Over here, FD, CA, this C can contract with a C here, and that will give you an A in there. And then over here, this C can contract with this C here, and put the A in there. See how there's a C down here, a C up there, a C up here, C down there. They contract out, they put A. I'm going to deal with that in a minute. So that gives us this object here. Notice A, and A here, and A here. Now this is very, very important. Very, very important. You mustn't lose sight of this part, otherwise the end result of this calculation, this proof, will be that you'll end up with a negative for the result you should have. So you mustn't forget this. So this A here and this A here, if we contract on the first and the fourth, this goes to 0. Okay, and we don't want that. This, if we contract, it won't help us, as it turns out. This A here and this A here, if we contract on that, this will go to 0, this will go to 0. That's not going to help us, and we'll end up with a result that's of no use. So what we can do is see the B here and the A, we can swap those using the symmetry properties of the Riemann tensor. If we swap those, this then changes the sign from plus to minus, and that's what's here. It's very important you do that. So here the B and the A have been swapped, BA, AB, and that all that does is swaps the sign. Over here, same thing here, we can't contract on the first and the fourth, so we're going to swap the indices, because you can contract on the first and the third. That's a non-zero result. So by swapping the B and the A, you can have AB, but that also changes the sign out front, the sign here. It's very important you do this, otherwise what follows on next will be useless to you. So by swapping the indices and changing the sign, you now have the one index up, the first index up, and the third index down, A and A, sorry, in the first and third places. You can contract on that. That's an allowed operation. Alright, so next line down we have this. Alright, now here the C, B, we can contract on the C here and the C here, and put the B in, so we get FBDE, which matches this one, by the way. And then over here, contract on the A and the A to give us the Ricci tensor EB, and that gives times delta FD. And then over here, contract on the A and that gives us RDB, delta FE. And that's all equal to 0. Alright, well let's just factorise out here the common factor of the Riemann tensor here, RFBDE, take that outside, n minus 1 in parentheses. And then over here we have this bit here. I'm going to take this over the other side, so it becomes negative here, delta FE. Could be taking this over the other side. I'm going to take this object over the other side, which becomes plus, and we have delta FD REB here, and minus Kronecker delta FE RDB. Okay, next line down we're going to multiply through by the metric with the lowered indices A and F, so that this F and this F can be contracted, and we can put an A down here. That'll be the next page over. Same here, multiply through by minus G subscript AF, the metric GAF, and we'll go over the page now. Keep this last line in mind. Here we are. When we do that, we get n minus 1 r a b d e, and over here we've contracted. There we go. We've contracted this object here. Now, one thing I do, I can swap a, b, d, and e, and that won't change the sign of the Riemann tensor, but it'll turn out to be useful, so I'll do that. Put that line in there. Nothing else here on the right changes at all. Then what we're going to do is we're going to multiply through by g, b, e, and g contravariant both indices up, the inverse metric, g, b, e, times r, b, a, e, d, and see b is in the first and e in the third, and the same on the right hand side there, just multiply through there, nothing else changes. And then we have n minus 1. Now what happens here, the b and this b contract, e and this e contract, n minus 1 r a d, and over here with these two metrics here, one up, one down, the inverse and the other, we use the Kronecker delta applies here, and the e's contract out, they sum out, and we're left with BA, so Kronecker delta BA. Don't forget to keep the minus sign here, RDB. Over here, GAD, GBE. Well, what will happen here, B and B, E and E, they'll contract out, and this gives us the Ricci scalar, curvature scalar, this one here. And over here, BA, this B and this B will sum out, and we're left with RDA. Alright, and over here, we have RAD n minus 1. Next line down we'll have n minus 1 RAD, and then over here the only thing will change these indices, because the Ricci tensor is symmetric, we can easily swap these indices without a change of sign. So DA here becomes AD plus GADR, the Ricci or curvature scalar. Now over here, just multiplying out the parentheses, this object, this one here, that one. Alright, same thing here, this one, minus GAD. Now see, RAD, we've converted that to GADR plus GADR. Now this term here on the left and this term here on the end cancel out, and then we bring this one over here to the right. So we have NRAD equals GADR, or the Ricci tensor is 1 on the dimension of the space times the metric times the Ricci or curvature scalar. Okay, so this result tells us that the Ricci tensor is proportional to the metric, and we can use this result to learn something about the Riemann tensor for a maximally symmetric n-dimensional manifold. And here we go, starting again. Let's go back to this result earlier here. Remember that one? And then where the RDB is, we're going to use the result from the bottom of the last slide and substitute in 1 on n, G, dB, dB times R. And over here, REB is 1 on n, GEB, R. Then what we'll do is factor out the common 1 over n times the curvature scalar here, and put the rest in parentheses, just with the negative terms on the right, positive terms on the left, and that's all equal to this. Now divide through by n minus 1, so we have the curvature scale divided n times n minus 1, times this product of metrics, of the metric inside here, so GAD, GEB, minus GAE, GDB. Right, and the only other thing is just I'll rewrite it in a nicer form that might be more familiar from textbooks and so on. B and E, because the metric is symmetric, we can swap the order of those two indices without a change of sign. So, and we'll also put the whole thing out front here. So we get GBE times GAD minus GAE GBD. Now notice here, BE, first index, third index, AD, second pair, AD, minus AE, the inner, and BD, the outer, the result you'd expect. Now, earlier we found that this was the other result we obtained, and so let's lower this index. Let's lower this index here by multiplying through by the metric GFA. So multiply across the parentheses there. Now, metric compatibility means we can take the metric inside next to the Ricci tensor. The covariant root of the metric is 0, so using the product rule, you'd see that we just get back to the metric times the covariant derivative of this object. So metric compatibility means we can put the metric inside the covariant derivative, minus this object here. Now, when we lower the index a here, put f, and here a, put f, we get this result here, equal to 0. Now, from the previous page, we saw that the Riemann tensor was equal to the Ricci or curvature scalar divided by n times n minus 1 times this arrangement of the metrics. So this applies in a maximally symmetric space. We have this result that the Riemann tensor is equal to this object here. So into this here, let's substitute then this result we got from the previous page. So remember, this here is equal to this Riemann tensor part here. Keeping the covariant derivative outside, same here, del b, keeping that outside, and we place this with the result from the very last page, which is the very last slide, sorry, the bottom of the last slide, which is this. Now all of that is equal to 0 because all of this is equal to 0. Alright, when we do that, here we go again, just reminding of the result. Now, let us perform. Now we know that the covariant derivative of the metric is 0, so there's no point differentiating all this because it's just 0. So the only thing that will be non-zero in here will be the covariant derivative of the curvature scalar. Minus, so here we go, so we get this result here. So all this stuff in here, in these square brackets, just factorizes out. Just take it right out because the covariant derivative of that will be 0. So we just, the only thing that's left of any that might not be 0 is the covariant derivative of the curvature scalar, here and here. Okay, let's multiply through by the inverse metrics to see if we can reduce this down to something else. So we want to contract all this down to something simpler. So let's choose GCD, GBE, and over here GCD, GBE, multiply that through. On the left hand side we've got 0 here, so that multiplied 0 is still 0. Okay, let's start contracting. So GCD with GFD. Well, the D's will go and we're left with CF, so Kronecker delta CF. GBE times GBE, that's just n the dimension. Minus, now GCD and this one will give us Kronecker delta CB. The CD here, BD here, the D's contract out, sum out, and we're left with C and B, so Kronecker delta CB. Likewise, BE and FE, well, the E's will go and we're left with B and F times that. And similarly over here, we carry on the same way, GCD with FD, and same thing again, and delta BC minus N, GCD times upper indices times GCD lower indices, well that just gives us N the dimensions of the space. GBE, GFE, again, Kronecker delta BF, we get this object here. Now, let's keep going, and notice, just notice here, B up, they will sum out, and we're left with Kronecker delta CF here. The B and the B sum out, leaving us with CF. Over here, C's go, and we're left with the B and the F, B and the F. And over here, n dimension times that. Okay, so here's this result here. Next line down, let's factorize out. See how that's Kronecker delta CF, Kronecker delta CF, and n minus 1. So let's take the Kronecker deltas outside here, and we're left with n minus 1 on top there. Over here, Kronecker delta BF, Kronecker delta BF, let's factorize that out, here it is, and we're left with minus 1 minus n, and we can rewrite that as plus n minus 1 over that. And we have here times this object here. Now if you have a look here, Kronecker delta CF, there's a C down and a C up. Over here there's a B up, B down. They're going to go, and we'll be left with the covariant derivative with the F index here, and over here covariant derivative with the F index, or the del with the F index. So next line over, here we go, the F and the F, and then this n minus 1 will cancel that one, this n minus 1 will cancel with that one, we're left with 1 on n del FR plus 1 on n del FR, so that's 2 lots of 2 over n del FR. This last result tells us that the Ricci scalar is everywhere constant on a maximally symmetric manifold of n dimensions. So if the Ricci or curvature scalar is everywhere constant, so we have constant curvature, so maximally symmetric manifolds have constant curvature. So for example, a sphere of fixed radius A has a Ricci scalar curvature of 2 on A squared. Well, derivative of 2 on a constant squared is going to be 0, and so that satisfies this condition here. So a sphere is a manifold of constant curvature. Alright, so finally we've found that a maximally symmetric n-dimensional manifold or space has a Riemann tensor given by, the Riemann tensor is the scalar curvature or Ricci scalar over n times n minus 1 times this combination of the metrics, so long, and where R is constant. R is constant. And notice here the order of the metrics down here, BE, first and third, first pair, A and D, second pair, minus AE, inner pair, BD, outer pair, as you expect the usual rule to be. And that is that.